Hello everyone, welcome back to my channel Maths with Smart Tips. Today in this video, we are solving the question paper of WBSET 2018 Mathematical Science question paper, and this is the question booklet series X. In this video, we are solving the first 20 questions of WBSET 2018 from question booklet series X. Now, before starting the solution of this video, I am requesting you to all those who are new in my channel, please like the video, comment if you have any doubt in the comment section below, and do subscribe the channel. So let's start with question number 1. And the WBSET 2020 papers first 30 questions are already solved in my channel. I will share the link in the description and also in the I tab, so you can check it out for those who are not seen the videos of 2020 WBSET. So let's start with question number 1. Question number 1 says that let fx equal to x square sine 1 by x plus exponential 1 by x minus 2 x not equal to 0 2 and 0 whether x equal to 0 2 has a removable discontinuity at x equal to 0, essential discontinuity, and these 4 options are given for this question. Now for removable discontinuity, we have the limit at that point of the function must exist but not equal to the functional value of the function for essential removable discontinuity. And for essential discontinuity, we have the limit at that point of the function does not exist. So first we check the limit at x equal to 0 and then x equal to 2 of the function fx. So limit x tends to 0 fx equal to limit x tends to 0 this function, and we know that the limit x tends to 0 this function goes to 0 and this function goes to exponential minus half. So this is equal to exponential minus half, and which is not equal to f0, and the value of f0 here is given that 0. Therefore it is clearly the example of removable discontinuity at x equal to 0 of the function fx. And now we check the limit at x equal to 2 of the function fx. Limit x equal to 2 x tends to 2 x square sine 1 by x plus exponential minus of 1 by x minus 2. This function x square sine 1 by x is continuous at that point, and this function is of the form, takes the form as limit x tends to 2 exponential minus 1 by 0, which is not exist at x tends to 2. Therefore this limit for this term, the limit at x tends to 2 does not exist. Therefore this gives the function has essential discontinuity at the point x equal to 2. Therefore option A is correct, the removable discontinuity at x equal to 0 and essential discontinuity at x equal to 2. Now the next question, question number 2, which of the following satisfies the hypothesis of Rolle's theorem? Here the function, 4 function is given. Now the Rolle's theorem states that let f from closed interval ab to r be a function such that condition number 1, if it's continuous and at open interval ab, if it's differentiable at open interval ab, closed interval ab, open interval ab, and the functional value of the end point of the interval will be same. Then there exists a point belongs to the open interval ab such that f dash c equal to 0. Now the first function is we check whether these 3 conditions is satisfied for the options or not. Now for the first option, mod x on minus 1 1, this is clearly continuous functions on minus 1 1, and we have to check the differentiability of mod x at minus 1 1. Now 0 belongs to minus 1 1, but the function mod x is not derivable or differentiable at x equal to 0. Therefore this is not satisfies the second condition of Rolle's theorem. So this is not satisfies the Rolle's theorem. Now option B says that fx equal to 1 minus mod of x minus 1 on 0 1. Now for this function we note that f of 0, that is this is we have to check this on the interval 0 1. Now the functional value at 0 gives 0 at x equal to 0 or for this function, and at x equal to 1 the right hand value of the interval of this function is equal to 1, which is these two are not equal. Therefore, the second option, the second function is not satisfies the third condition of the Rolle's theorem. Therefore, this is also not satisfied the Rolle's theorem. Now, option C is given that this 1 minus x minus 1 power 2/3 on 0 2. Now, we check these two are not equal at the third condition of the Rolle's theorem. Also, you can check the remaining two conditions for the options. It is just so to show that this is so satisfies or not. Now, so for this is also not satisfies the conditions of Rolle's theorem. And in option D, this is clearly a polynomial function which is clearly continuous and differentiable throughout R and so on this interval minus 2 2, and we check the functional the value f equal to f, that is f of minus 2 equal to, this gives minus 8 plus 8 which is equal to 0, and f of 2 equal to, also this gives 8 minus 8 which also gives. Therefore, this function satisfies the three conditions of Rolle's theorem. Therefore, this is satisfies the hypothesis of Rolle's theorem. So option D is correct here. Now, the next question is, let f from fg from ab to ab be any two continuous functions ab belongs to R such that infimum of fx and infimum of gx are equal for x belongs to this interval. Then which of the following statements are correct? First, we take the interval ab equal to 110. Now, take the functions fx equal to x minus 1 and gx equal to x square minus 1. Now, then f and g both increasing function, these two functions clearly increasing on this interval, and so infimum of these two functions attain at the lower end point of the interval. That means the infimum attain at 1 for both the functions. Therefore, infimum of fx equal to at 0 point at 1 point attain its so this is equal to 0 since x minus 1 is function x equal to 1 point. And similarly, the infimum of the function gx at x belongs to 110 is equal to 0. But the two functions are not equal in general. Therefore, this option is not correct. Equal function. Also, the function D is not correct. Now, but at x0 equal to 1, f of x0 equal to 0, since at x equal to 1, f of 1 equal to 0 and g of 1 also equal to 0. But this is not the unique point, because if we take another function which is of higher degree, then we can take then we can get also many such x0 for which this condition is satisfied. Therefore, this option is not correct. There exists at least one x0 belongs to AB such that fx0 equal to gx0. This option B is correct here. Now go to the next question. Question number 4 says that let f equal to root under mod xy belongs to R2. Then the four options are given here. First, we check the continuity of these functions. Now, take x equal to r cos theta and y equal to r sin theta, r greater equal to 0. But root under mod of xy equal to this r square sin theta cos theta, and which if we multiply divide by 2, then we get r by root 2 sin 2 theta. Now, sin 2 theta is bounded on 0 1, and at r tends to 0, fxy tends to 0. Therefore, fxy is continuous at x equal to 0. Therefore, option D is correct here. Also, remaining three options necessarily not correct. So, also you can check. It is a famous problem. Mod of xy to the power p is differentiable at 0 0 whether this p is greater than half. This is a most famous problem of function of several variable. So, but here the value of p is equal to 2, that is square root. So, this is not differentiable. Now, if we check the option B and C, that is directional derivative and the first order partial derivative, then we get fx00 equal to f of a0 minus f00 by h, whether f equal to this, which gives 0, and similarly fy00 is also equal to 0, which are constant. Therefore, this option is not correct. And also the directional derivative along the point, the function, the formula for checking directional derivative is f dash c equal to, here u is the unit direction vector and c is the point at which we have to check the directional derivative. So limit h tends to 0, f of ac plus hu minus fc by h, which is equal to this. If we take the point u equal to ab and c equal to x0 y0, then we get this formula. You can check the formula using this formula, and obviously you cannot get any directional derivative for the point 0, 0. So this option is incorrect. Now we go to question number 5. Let f from c to c be an entire function with f0 equal to 1 and f1 equal to 0, then the maps. These 4 options are given. Now here we use the open mapping theorem. The statements of open mapping theorem says that let D be a region, and suppose f is a non-constant analytic function on D, then for any open set U in D, fu is open. That means image of a open set is open. The open mapping theorem says that. Now there is two conditions. There are two conditions. One is non-constant and second one is analytic. Here it is given that the function is entire. That means it is everywhere analytic. But the constant, this question does not assure that the function is non-constant. But there is two conditions, f0 equal to 1 and f1 equal to 0. Suppose if fz is a constant function, then fz gives same value for any z. But here it is given that for two different value of z, f gives two different values. Therefore, these two conditions assure that the condition must be non-constant function. Therefore, applying open mapping theorem, we get open sets in C into open sets in C. F maps. This is necessarily correct option, and remaining are incorrect option. And here the D is the domain is complete C. Now go to the next question, question number 6. And before starting the solution of this question number 6, I am requesting you to all those who are new, please subscribe the channel and share with your friends, and do comments in the comment section below if you have any doubt. Now question number 6. Let f be analytic function in a neighborhood of 0 having a 0 at 0 of order 5 and g has a pole of order 3 at 0. Then first we take z. Since g has a pole of order 3 at 0, then we can take gz equal to 1 by zq. And now 1 by zz equal to zq, which has a 0 of order 3 clearly. And since given that fz has 0 and 0 of order 5, therefore we can take fz equal to z to the power 5. Now fz by zz, that is fz into 1 by gz equal to z to the power 5 into z3. This gives z to the power 8, which has clearly zeros of at z equal to 0 of order 8. So this is a simple question of complex analysis. So option A is correct here. Next question, question number 7. Question number 7, the function fz equal to exponential z by z minus 1 square has no singularity, essential singularity, double pole. Now pole means what? Pole means we must have limit z tends to 0 at a point z0. Poles of a function gives the limit is equal to infinity. But in case of essential singularity, the limit of that point does not exist. Also, we can check the essential singularity through Lorentz series. Infinite number of terms in the principal part of the expansion of Lorentz series. If we have infinite number of terms, then the singularity is essential singularity. Now, here it is given that at limit z tends to 1, exponential z by 1 z minus 1 whole square. Now we have z by z minus 1 means whole square means at limit z tends to 1, or you can take z also. At z tends to 1, this gives 1 by 0, which is infinity. But in case of exponential power z by 1 minus z minus 1 whole square, at z tends to 1, this gives exponent of the form this, which does not exist. Therefore, this is clearly give the essential singularity at z equal to 1, and remaining options are incorrect. Not pole, singular, double, not pole. The point at z equal to 1, it does not give a singularity pole. Now, next question, question number 8. Question number 8 says that which of the following function is analytic fx equal f of x plus iy, that is fz equal to 6x plus 5. Now to check analyticity, to check whether a function not analytic, we have to check a function. If a function does not satisfy the CR equation, then function is not analytic. If a function is not harmonic, then it is not analytic. These two conditions. Also, now first we go to option A. Option A says that fz equal to 6x plus 5. We can write 6x equal to, that is 6 and real part, then z plus z bar equal to x plus iota y plus x minus iota y, and this gives 2x, and if we multiply by 3, then this gives 6x. So we can write 6x equal to 3 into z plus z bar, and we apply here the complex form of Cauchy-Riemann equation, that is del f del z bar equal to 0. This is the complex form of CR equation. If this f satisfies this equation, then we say does not satisfy, then we say that this is not analytic. Now del f del z bar equal to 3, which is not equal to 0. Therefore f does not satisfy the CR equation. This gives f is not analytic. Option number B, given that exponential 2ix, which is equal to exponential e to the power exponential I2x, and this is equal to cos 2x plus iota sin 2x. You can take u plus iota b fz equal to, then u equal to cos 2x, v equal to sin 2x, and the Cauchy-Riemann general Cauchy-Riemann equation is ux equal to vy and uy equal to minus of vx. This is the general Cauchy-Riemann equation. Now we have to check whether the function f satisfies the Cauchy-Riemann equation or not. If not satisfied, then it is not analytic. Therefore ux equal to minus 2 sin 2x, but vy equal to 0. There is no terms of y, so this gives 0. So ux equal to vy is does not satisfy, therefore it is not analytic. Therefore option A and B are incorrect, not analytic. Now we check option C. It is only the imaginary part, v equal to this. So ux and uy both 0, and vx and vy gives the function, and it is clearly ux is not equal to vy, therefore it is not satisfies the Cauchy-Riemann equation, therefore this is also not correct option, and clearly option D is correct here. Also you can check the option D as follows: 1 plus 2 into x plus iota y, so this is equal to 1 plus 2z, which is clearly analytic function. Now the next question, question number 9, any group of order 25 is. Now first we apply here any group of order p square where p is a prime number is an abelian group. Therefore this group of order here p equal to 5, which is abelian group. Therefore, and here also we use that the order of group less than 1000 which are simple are 60, 168, 360, 504 and 660. These are the groups which are simple of order less than 1000, but the order of the group is here 25, therefore it is not a simple group, therefore it is abelian but not simple. Option C is not necessarily normally correct statement, correct option. Now question number 10. Question number 10 says that let C01 denote the ring of all real valued continuous functions over 01, and psi from C01 to R be a map such that psi of f equal to f0. Let us take a function fx equal to, then these four options are given here. First let us take the functions fx equal to x. You can take also fx equal to a constant function, also you can take fx equal to constant function. Now psi of fx equal to f0, psi of f equal to f0 we apply here. So psi of fx equal to f0, and f0 gives here simply 0 for all x belongs to 0, and therefore psi x equal to 0. Therefore now we have used the result here that R equal to C01 be a ring of real valued continuous functions on 01. Let m equal to f belongs to R such that fx equal to 0 for all x belongs to 01. Then m is a maximal ideal of R. Therefore we apply this result in this question, we get psi is an maximal ideal of R. But here the option 2 it is given that without being maximal ideal, therefore it is not correct. And also apply the concept of ring homomorphism, simple definition: if f from R to R dash such that f of x plus y equal to this, f of x plus fy, and f of xy equal to this. For phi is x, psi is equal to 0, or you can take for fx equal to constant, then clearly and simply this satisfies these two conditions, which is clearly a ring homomorphism. Therefore option A is clearly correct here. Psi is a ring homomorphism onto R, and kernel of this is maximum everywhere. From this part also you can say this is correct statement, and kernel of psi means here this x gives the kernel, since for x belongs to this, psi x gives 0. So here the A option is correct and these two are remaining incorrect. Now we go to question number 11. Before going to question number 11, watch the video till the end. Please like, comment and to subscribe the channel. Question number 11 says that fx equal to x cube plus x square plus 2 and gx equal to x cube plus x plus 2 over this z3. Then z3x is reducible or reducible, we have to check that. Now the function fx equal to x cube plus x square plus 2. Now the elements of z3 are 0, 1 and 2. Therefore f of 0 equal to 2, f of 1 equal to 1 plus 4, and f of 2 equal to 14. Now if we apply modulo 3, since this is z3, therefore this is equal to 2, this is equal to, if we apply modulo 3, then this is 1 and this is 2. Therefore these three are non-zero. Therefore f is clearly irreducible. Now we check for g. Gx equal to x cube plus x plus 2. Now g0 equal to 2. If we apply modulo 3, then this is also gives 2. Now g1 equal to 4. If we apply modulo 3, then this gives 1. And g2 equal to 12. Apply modulo 3, this gives 0. Therefore we get a 0 here. Therefore g is not irreducible. Therefore f is irreducible but g is not irreducible. Option B clearly correct here. Next question, question number 12, says that if R is a ring with unity, then AB belongs to R such that AB equal to 1, BA is idempotent, and 1 minus BA is idempotent or not. The definition of idempotent element is says that A square equal to A. If any element satisfies this condition, then we have the element A is idempotent element. Now we check idempotency for BA and 1 minus BA. Now BA square, and here it is given that AB equal to 1, BA into BA, this is equal to BAB A, this is equal to BAB means 1 here, so this is equal to clearly BA. Therefore BA square implies BA, so BA is idempotent element. Next 1 minus BA square equal to 1 minus BA into 1 minus BA, this is equal to 1 minus BA plus BA into BA. So this is equal to 1 minus 2BA plus BAB into A. This is equal to 1 minus 2BA plus AB equal to 1 given identity. So this is equal to BA. So this is equal to 1 minus BA. Therefore 1 minus BA square equal to 1 minus BA. Therefore both the elements BA and 1 minus BA are idempotent elements in R. This is D option correct here. Now go to the next question, question number 13. 13 says that if A is an orthogonal matrix of order 3 with three non-zero eigenvalues alpha 1, alpha 2 and alpha 3, then the eigenvalues of A inverse. Now that from the definition of orthogonal matrix, we have A transpose equal to A transpose A equal to identity. So if we take any of these, then we must have this relation A inverse equal to A transpose. Now we have a result that eigenvalues of A equal to eigenvalues of A transpose, and from this result we have eigenvalues of A inverse equal to eigenvalues of A transpose. Therefore eigenvalues of A inverse are same as the eigenvalues of A. So clearly here these three are the also the eigenvalues for A inverse. Now question number 14. Question number 14, let A and B be real invertible matrices such that AB equal to minus B. Then the fourth option based on trace of the matrix. Now we use two properties related to trace here. For the first one is trace of AB equal to trace of BA for any square matrix of same order AB and B, A and B, and result number 2, trace of any constant K into A equal to K into trace A. Now given that AB equal to minus of BA, taking both sides trace of the matrix and trace of AB equal to trace of minus BA, and apply this result, we get minus trace of BA. Now trace of BA equal to trace of AB from first result, therefore get trace of AB equal to minus trace of AB. This gives 2 trace of AB equal to 0. This gives trace of AB equal to 0. Now the only restriction of the matrix A and B is that A and B are real invertible matrix. Therefore case 1, from this we take A equal to I3. So I3 is real matrix and also invertible matrix. Therefore trace of, put the value A equal to I3 in this equation. So trace of I3 into B equal to 0, and which gives trace of B equal to 0, since B into I3 or I3 into B equal to B. And if we take B equal to I3, then this is equal to trace of, from this we get A into I3 equal to trace of A equal to 0. Therefore trace of A and trace of B both are 0. Option A is correct here and remaining are incorrect. Now the next question, question number 15, says that two subspaces of R4 are given by U and V. Applying row operation, we get this U and V, these three vectors are clearly linearly independent vector. We can check this. This is just simple calculation. Apply row operation, and lastly we find that the 3 non-zero rows are non-zero. 3 rows also non-zero. So this gives the rank of dimension, means number of element in U. So dimension of U equal to, here clearly 3, since the 3 vectors are linearly independent. Also similarly, if we apply here, so the dimension of V equal to, here also 3. You can check to this. I already checked, but this is a great big calculation, so I don't write it here. And now the dimension, since U and V are two subspaces of R4, therefore dimension of U union V is equal to 4 here clearly. Now we apply a formula, dimension of U union V is equal to dimension of U plus dimension of V minus dimension of U intersection V. We have to find the dimension of U intersection V, and we already known the value of these 3. Therefore we can find dimension of U intersection V. This is equal to dimension of plus dimension of V minus dimension of U union V. So this gives 3 plus 3 minus 4, and this is equal to 2. Clearly the option B is correct here. Now the next question, question number 16. Before going to the question number 16, I am requesting you to all, please like the video, comment if you have any doubt in the comment section, and to subscribe the channel. Question number 16 says that, this is says that which of the following is false in metric space. It is noted that we have to find the false statement for this 4 statement in the metric space XD. The first result is A and B. I think it will be comma here, such that A is compact and B is non-compact but closed in X. Then A intersection B must be compact. Yes, this is correct statement. Since we know that this is theorem, if A is compact and B is only closeness, we only need the closed part, then A intersection B is compact. So this is correct statement. So this is not the false statement. A closed subset of X need not be second category in X. This is also a statement. This is correct statement, and this is not false statement. The option number C, if closed and bounded subset of X is compact in X, we have to check option C and D. And in option D it says that every compact subset of X is closed and bounded. Yes, this is also a statement of theorem, so this is correct. So you can take clearly, sorry, this is the correct statement. So this is not false. So the false statement is only option C, every closed and bounded subset of X compact in X. To check option C, let us take the matrix space QD and A be the subset which is closed and bounded. Take A equal to closed interval root 3 intersection Q. Clearly, A is a subset of arbitrary union of root 2 minus 1 by n, root 3 plus 1 by n. So no finite subcover of this infinite cover can be cover set A. Therefore, A is not a compact. Therefore, A is closed and bounded, but A is not compact. Therefore, this is the false statement. Now, the next question, question number 17. It says that let x1 equal to c over 0, and that means continuous functions, real valued continuous functions over 0 and d1, and this is also d2, d1, d2 are two metric, given that suprema metric, and this is integral 0 to 1 mod of this metric, and it is given that the four option complete about completeness. Now, to solve this question, there is a theorem. This question based on directly theorem based questions. The space CAB of all continuous real valued function defined on AB with the metric d infinity AB, that means maximum of t belongs to AB mod of this, that is suprema metric, is a complete metric space. Therefore, x1 is complete metric space. Therefore, the option C is not correct. And to check whether x2 is complete or not, we have to check. Actually, complete means what? Complete means every Cauchy sequence of that metric space converges to a point which is belongs to that metric space or that subset X, this set X. Every Cauchy sequence is convergent in X. Now, take a Cauchy sequence xm t equal to 0 whether this m into x minus half whether this and 1 whether this, where xmt are the sequence of all continuous functions on 0 1. xmt are a sequence of continuous functions, therefore the limit function must be continuous, but we check that the limit function of this is not continuous, therefore the function is not convergent. Therefore, and whether it is a Cauchy sequence, but it is a Cauchy sequence. Or xn is a Cauchy sequence d of xn xm less than epsilon for all mn greater than 1 by epsilon. D of xn f equal to integration 0 to 1 this integral, the three integrals divided from the definition of this function xt, and these three are modulus function, therefore these three integrations are non-negative integrals. Now d of xn x tends to 0 as m tends to infinity, therefore each integral tends to 0. Since xt is continuous, so we have xmt, so xmt is continuous, so we have xt, the limit function, which is not continuous. This is not continuous, therefore the sequence xmt does not convergent, therefore xt is not a complete metric space. Therefore x1 is complete but x2 is not complete. B option is correct here. Go to the next question, question number 18. Question number 18 says that if X be a non-linear space and x0 belongs to X, such that for each bounded linear functional f on X with norm f equal to 1 and mod of f is equal to k. Now, we solve this question. Here, fourth option is given about norm of x0. The linear functional f on a non-linear space X norm is called bounded if and only if there exists a positive constant k such that mod of fx is equal to k into norm x for all x belongs to capital X. And we defined norm of fx equal to supremum of norm x not equal to 0 mod x by norm x. Now, here it is given that norm of f equal to 1 in our problem. Therefore, we put this, and since this is supremum of f mod of x0 minus fx and given that this is less equal to k, so we can write this is less equal to k by norm of x0. Now we put the value of norm f equal to 1, this is equal to k by norm x0, we get norm of x0 less equal to k, since norm of x0 is a positive quantity. Therefore option is A is correct here. Now go to the next question. This is also the statement based question. Which of the following is true? I have a theorem for this question. A Hilbert space is separable if and only if it has a countable orthogonal basis, or you can take a linearly independent countable orthogonal basis. Moreover, if H is separable, then all orthogonal bases of H are countable. This is a theorem. So from this theorem directly we can say that here the option D is correct here. A Hilbert space is separable if and only if there exists a complete countable orthogonal set in X. And orthogonal means linearly independent, orthonormal means linearly independent. So from this is the correct statement. And question number 20 says that this is also a statement based question, theorem. It is also based on a theorem directly. If an orthonormal set in a Hilbert space X, then here is a statement that is if E is complete if the linear half of E is dense in X. This is correct statement based question directly. So how was the video? If the video is helpful for you, then please give a like to this video, share with your friends and subscribe the channel. So thank you friends, see you again in the next video. Thank you.